Everybody on Zoom, please welcome Lijing Wang, who is right now a research fellow at the Harvard Medical School and is doing really interesting work in infectious diseases.
Thank you, Professor Geller. Then, hello everyone, welcome to my research talk today. The title is Artificial Intelligence Solutions for Reliable Epidemic Forecasting, but actually I will also cover my other research topics in the machine learning, the general domain, machine learning, deep learning. So I'm interested in the broad topics of computing for social good, with an emphasis on applying machine learning, deep learning, and natural language processing for solving the societal challenge, such as in epidemics, in bioinformatics, or in public health. And my research works cover topics from machine learning theory and algorithm to downstream frameworks and methods, and also further apply to the applications. So first, I applaud the new machine learning theory and algorithm. They are used to advance the AI-based forecasting system in a general domain, and it has been deployed and applied to many downstream applications and methods. Second, so my PhD thesis topic is the artificial intelligence solutions for reliable epidemic forecasting. More specifically, I propose the deep learning-based methods that can generate more accurate and explainable predictions for the epidemic dynamics. Then my current work at Boston Children's Hospital and Harvard Medical School focus on applying the NLP technology for the clinical narrative extraction tasks. More specifically, just to investigate the fine-tuning strategy by using the transformer for the relation extraction from the clinical narrative. So that's one of the example of my current research work. Then all the proposed algorithm and the framework methods has been applied in multiple online systems, including the biocomplexity forecast dashboard, the CDC Epidemic Predictive Initiative for both the seasonal influenza and COVID-19 dynamic forecasting, and also the proposed algorithm is applied in an online truck repair system. And in today's talk, I will mainly focus on two papers and will have a brief introduction to the other works. Paper one is focus on the machine learning theory and algorithm. It was proposed in a general domain, and I will show its application, its deployment in the other applications. And paper two focus on the epidemic forecasting using graph neural network. I just broadly, I hope my research talk and our research work will spark more interest in applying AI for social good. In the talk, there are totally 5 sections. Section 1 will talk about paper 1 in the general domain. And section 2 will discuss the paper 2 in epidemic domain. And then section 3, I will introduce the other works in epidemic forecasting. In section 4, I will briefly overview my current work in clinical analysis domain. Then finally, I will conclude my work and discuss the future research directions. In section 1, so as we transfer from the basic research to production-ready AI models, there's more emphasis than ever on building trustworthy AI system for reliable outputs. In the context of real-time forecasting, then the forecasting model are usually periodically retrained when the new observations come in. But there's no guarantee that the different generation of a model can be consistently correct when given the same input. So it is based on this motivation that we introduce a new concept of learning model. It's called the consistency. So consider a cancer diagnosis system. Given a patient information, then the system output a correct prediction. Then after the new data become available, the system is updated. Then given the same patient information, the system give a wrong prediction. Then this inconsistent behavior is very dangerous in many application and system, such as the car evaluation, safety evaluation system, or in the disease diagnosis system. There's no previous work has been formally discussing this problem, and we're the first one to defend consistency of a learning model and provide a solution to improve the consistency of a learning model. We define the consistency as the ability of a model to reproduce an output for the same input after retraining. There are 4 scenarios before and after retraining a model. Here, scenario A and D are case of consistent behavior, and C is a case of accurate behavior, and A is a case of correct, consistent behavior. And in practice, we actually want to improve the correct consistency and accuracy. So the question is how to improve them. We can say the ensemble learning. So the ensemble learning method combines the prediction from multiple trained learners to reduce the variance of prediction and also to reduce generalization error. Our intuition of using ensemble is to leverage the models from local optima models and to coverage a greater area of the feature space so that we can get consensus for the final prediction. So here we assume that a supervised classification problem has P-class labels. Then we represent the prediction and ground truth vectors in P-1 dimensional probability simplex. The ensemble is the averaging of all single learners, and the model will be retrained at time t and time t+1. We call it 2 generations. In this assumption, the consistency of a model is represented as the Euclidean distance between 2 prediction vectors from 2 generations. And correct consistency is computed as the sum of distance between 2 prediction vectors and the ground truth vector. Then the accuracy is represented as the Euclidean distance between the prediction vector and the ground truth vector. So based on the Minkowski inequality, we prove theorem 1 and theorem 2 that the consistency and correct consistency of ensemble learner is not less than the average consistency and correct consistency of single learners. And we also prove theorem 3 that a better aggregate level correct consistency performance of ensemble can be achieved by combining components with accuracy that is higher than the average accuracy of the ensemble members with a quantifiable probability. And there are some other theorem and the proof which can be found in the paper. If you are interested, we can discuss this after the talk. Then based on the theoretical findings, we propose a new dynamic snapshot ensemble methods. The main idea came from Huang's work that instead of training multiple single learner independently, we save multiple single learner during 1 training process so that we can obtain ensemble components in a very efficient way. Then just based on this main idea, in our algorithm, the model adopts a cosine function to change the learning rate and use a cyclic snapshot strategy to periodically save the local optimal trained learners from 1 training process. Then similarly, we also propose to use stepwise decay learning rate schedule and save top N trained learner during 1 training process. So these are 2 variants of the proposed method. So more importantly, in our framework, we propose a pruning algorithm. This pruning algorithm can help us to select good single learner, which can improve the performance of the ensemble learner in both accuracy and correct consistency. And according to the theoretical findings that we proposed previously, then here beta is the prune factor. We actually, in practice, we can compute an ideal beta, which can guarantee an improvement in the final ensemble learner accuracy and correct consistency. So this is the framework of the whole algorithm. It will just randomly shuffle the training and validation data set so that it enables the data diversity. And then by random initialization of the model parameters, it enables parameter diversity. And by using the dynamic pruning algorithm, we can make sure that we choose the good single learner from the single learner pool and to improve our ensemble learner performance. Then by using this dynamic pruning, we can also just achieve a good performance, but with much less computational cost compared to the traditional ensembling method. And we define our own metric, CON, to evaluate consistency. It is defined at the macro, it's the individual prediction level. And then ACC-CON is the metric for correct consistency. ACC is the accuracy. And we conduct the experiments on classification data sets, include CIFAR-Turn, CIFAR-100, and Yahoo Answer. The base models are ResNet and FastText. So this table shows the experiment result, and we can observe that compared to the single model, that all the ensemble models actually significantly improve the forecasting performance in both ACC CON and ACC CON. Then so here the ACC improve as high as 8%. This is very impressive. And CON improve as high as 18%, 19%. ACC CON improves as high as 14%. And our method here highlighted by the red color, our methods achieve comparable performance with the best one, which is the extend bagging method, but with a much smaller training time. Here shows that. So we also conduct the sensitivity analysis on the ensemble components number and also on the prune factor beta value. So the sensitivity analysis results show that by combining more components in the ensemble learner, it can achieve better forecasting accuracy and correct consistency. And also this result shows that the proposed pruning algorithm can achieve a good trade-off between model performance and training cost in practice. In this work, we proposed the new theorem and new algorithm, and also presented the demonstration on image and text classification data size. So the proposed algorithm is model agnostic and computational efficient. The experiment results show that the proposed method can significantly improve the forecasting accuracy and correct consistency. So far, I have introduced the work in a general domain for the machine learning theory and algorithm. Then in section 2, I will introduce the paper 2, Causal GNN, which is short for causal-based graph neural networks for spatial and temporal epidemic forecasting. Before I go into the paper details, I'm going to give an introduction about epidemic forecasting and existing methods. Infectious disease can spread directly or indirectly from one person to another, and based on the spreading scope and pervasiveness, it can lead to an outbreak, an epidemic, or pandemic, such as the seasonal flu, the Zika, Ebola, and the ongoing COVID-19. So to be consistent, I will use the epidemic in the following talk. However, the methods or algorithm proposed in our work can be used interchangeably across the skills. So the epidemic has placed a heavy health, social, and economic burden on our society. To produce the timely, well-informed, and reliable epidemic forecasting is crucial for the public policymaker to make a better decision. So let's first understand what is epidemic forecasting. A general idea is to use the observed data source as the reference data and to make spatial and temporal predictions of an epidemiological target. And this is done by a forecasting model, and the model is what we are focusing on. Here are two examples. The first example is organized by CDC from the year 2013. So CDC organized the flu site challenge. The participants are required to submit a short-term trajectory of influenza-like illness, and also provide the peak intensity and peak week forecast every week along the flu season. And another example is the COVID-19 forecasting challenge. So CDC organized this challenge so that all the researchers from all over the world can contribute to the current forecasting effort. The participants are required to submit the 1 to 4 weeks ahead forecast at the confirmed case count, death count, and also death count, and also hospitalization. So the forecasting resolution, spatial resolution, include the global, national, state, and county levels. Forecasting epidemic has been an area of active research over the past couple of decades, and existing work are mainly in 3 categories. The first is mechanistic methods, the second is statistical time series methods, and the third is deep learning methods. So the first methods, it includes the single patch or network-based compartmental models, as well as the agent-based models. This model leverages a mathematical model of disease transmission and to capture the dynamics of epidemics. The underlying disease model can be SEIR, SEIR, or their variants and extensions. So the forecasting is made by calibrating the disease parameter using simulation optimization and to match observations, and then by projecting the most recent parameter to make the future prediction. However, just by using this model, calibrating especially for the geographical high resolution is really challenging, just given the need to capture the time varying inter and regional effects. The second are statistical time series methods. They employ time series based methodology to learn patterns from historical data and leverage those patterns for forecasting. However, these methods rely on the stationarity assumption of the time series data. But during the new emerging epidemic, the data usually is non-stationary. So these methods are not effective in accurate forecasting during those phases. Then, given the advance in deep learning model, they have gained increased prominence in epidemic forecasting. It is actually a relatively new emerging research direction. Like the first FNN, RNN, CNN that applied for epidemic forecasting in around 2017 and 2018. Then we proposed the first graph neural network for epidemic forecasting in 2019. And in Causal GNN, now I back to this paperwork. In Causal GNN, we focus on graph neural network-based epidemic forecasting. the motivation behind this work is that a deep learning model usually barely consider the epidemiological context, thus it's difficult to explain the learned model and predictions, and usually overfitting to the limited data, training data. On the other hand, a theory-based mechanistic model can provide the epidemiological context because it can capture the diffusion patterns of disease spread through some detailed simulations. Then a framework to combine deep neural network with the theory-based mechanistic model is promising to provide a more accurate and explainable predictions. Last, we propose causal GNN. So we assume we have n reasons in total, and we formulate the data structure as a graph. In each graph, let a node represent a reason, and each node is associated with the disease dynamic at the node level, and also such as the demographic information at the node level. Then the nodes are connected via adjacency matrix. This adjacency matrix can be defined by such as the geographical adjacency, by human mobility flow, by model-generated flow, or by learned hidden coefficients. And in this work, we leverage the attention mechanism to learn the hidden coefficient between the nodes and to propagate the node embedding over this adjacency matrix. So based on the sighting, at each time point t, we create a graph that is associated with a feature matrix CT and adjacency matrix AT. Then given a historical key time points of the graphs, the objective is to predict an epidemiological target for each region at a future time point t plus h, and h is the forecasting horizon. In our experiment, the epidemiological target is the COVID daily new confirmed case count. So we propose a causal-based graph neural network. The proposed model can be roughly divided into two parts. The attention-based dynamic GNN module that can capture the spatial and temporal dynamics. And then the other module is the causal module which is SEIR compartmental module that run at the node level. That means each node will run their own SEIR simulation. So the two modules mutually learn from each other via causal encoder and causal decoder layer. This is the framework of causal GNN. And more specifically, at each time t, a graph will be embedded where a series of nonlinear transformations include the causal encoding, feature encoding, dynamic graph encoding, temporal encoding, causal decoding, and causal SEIR computation. And finally, there's an output layer. So QT here represents the causal feature matrix. It includes the causal generated, such as the case count, confirmed case count, the recovered case count, the death case count. And then this QT is embedded where a causal encoder layer. Then the node feature is embedded where a feature encoder layer. Here in the dynamic graph encoding layer, like the temporal, temporal encoding, this AT is the adjacency matrix. It is a attention-based matrix that we leverage the addition attention to compute AT. And then tilde HT is the temporal embedding. I will introduce this in the next slide. So the temporal embedding will propagate over the graph where this AT and get the spatial embedding HT. The temporal embedding here is to concatenate the embedding from the causal feature, from the node input feature, and also the spatial embedding from the last time point. And the causal through a temporal encoder layer, we obtain this temporal embedding tilde HT. Then the tilde HT will be fed into the causal decoder layer to generate the model parameter PT. PT will be used to run the SEIR simulation one step further and to generate the causal features for the next step computation. And at the output layer, we concatenate the spatial embedding with the causal embedding and make the final prediction. This is a brief overview of how each module works together. So at each time t, the input feature, causal feature, and the temporal embedding feature at the previous time step are encoded and updated. Then these hidden embeddings are concatenated and encoded by a TE layer. The updated TE embedding is then decoded as simulation parameter PT, and then we run SEIR simulation one step further. This will be repeated k times, and the key, as I introduced, is the historical time step in the input sequence. Then at the last time step, the causal parameter at time t are used to run SEIR simulation is minus one step further and to generate the causal feature at the future time point. And the causal feature at the future time point will be concatenated with the spatial embedding at the last time step to make the final prediction. And we add the causal feature to the loss function to regularize our prediction. We evaluate the proposed framework for forecasting the daily new confirmed case count of COVID-19 at global, US state, and US county levels. And we compare the proposed model with a broad range of baselines, including the causal-based causal model and also time series model, as well as deep learning models. So these plots show the model performance of MAE computed across all locations at various prediction dates. And we can observe that the model performance varies across date, but our model performs the best in most of the days, which highlighted by the black color here. And to explore the different components in the proposed model, we conducted the ablation study. We remove the causal model and also remove the attention mechanism separately, then to implement the ablation models. And compare with the ablation model, the Causal GNN performs the best. So this indicates that all three components played an important role in improving the final model performance. And among the three components, that the graph structure plays the most important role in improving the long-term forecasting performance. And more details can be found in our paper. One of the highlights of Causal GNN framework is that it can generate a meaningful epidemiological context for future forecasting. Here, the plot shows the black line is the ground truth, and the orange line shows the causal module generated curve, and the blue dot is the prediction by our model. The red cross is the prediction by our model, but removing the causal module. We can see that the causal module can provide a meaningful epidemiological context, which the curve is similar to the ground truth, the input ground truth. And then the prediction by our model performed better than the prediction without the causal module, which shows the importance of the causal module in our framework. So the proposed framework combines the graph neural network with the theory-based mechanistic models. Then, so it considered the spatial temporal signal as well as the epidemiological context, thus leading to better forecasting accuracy and explainability. So in section 2, I introduced paper 2 in epidemic forecasting. Then based on the same background, I will briefly introduce the other works in epidemic forecasting. Actually, there are many other challenges when using deep learning methods for epidemic forecasting. The first is the lack of spatial temporal correlations. The disease spreads over a contact network, which depends on human mobility behavior. So under this case, if we only use the traditional time series models such as ARIMA or LSTM, they do not consider the spatial signals, thus fail to capture the disease spread in the spatial context. So a graph neural network is promising to capture both the temporal and spatial signals. Thus, we investigate the graph neural network-based framework for epidemic forecasting. Along this research direction, there are 2 works. The first work is mobility GNN. Similar to causal GNN, we build the graph structure as a graph, and then we leverage the Google COVID-19 aggregated mobility research data to build the network structure. So here, the node feature and edge feature are embedded via LSTM layer, and then the embedded information propagate over the graph through the recurrent message passing using this Google mobility data map. So we experiment the proposed model on forecasting the COVID-19 confirmed case count, and the results show that using this dynamic mobility map, the GNN outperformed the other GNN model using such as the static mobility map or using the traditional commute flow map to make the network structure. Along this research direction, another work is Causal GNN. In this work, it leveraged the attention mechanism to learn hidden coefficients between nodes and then combine geo-adjacency matrix with attention matrix. We call it the location-aware attention matrix to build the graph structure. So this work also proposed because such as the Google mobility data sets is usually not public available for people to use. So by using this attention mechanism, we can all implement this graph structure for the future use. So the model, in this model, the node features are encoded via RN layer and also by a multi-scale dilated convolution module. So we tested the model on 3 influenza data sets and demonstrate that it outperformed the existing spatial temporal forecasting methods. The second challenge is the lack of epidemiological context in deep learning model. We already introduced this background in Causal GNN work. Then another work is called TDEFC. TDEFC is proposed at the context of the influenza-like illness forecasting. So traditionally, CDC provides the LI surveillance data at the state level. However, given the heterogeneity between the subregions, the public policymakers want to know the IOI dynamics in the subregion, such as the county level IOI dynamics. Then, since there's no county level surveillance data, using the traditional data-driven methods is not feasible because there's no training data. We consider that because the theory-based causal model can generate the synthetic data, so we propose this TDEFC framework. In this framework, we combine and we use agent-based SEIR simulator to calibrate on the observations and then to generate synthetic training data for our deep learning model to train. So the deep learning model trained on this synthetic data can actually learn the patterns from some unseen data patterns from the real data. And also, one highlight of this framework is that it enables the what-if forecasting. One scenario is that in the simulation process, we can incorporate different interventions in the simulation. Then we generate the context-specific synthetic training data. The model that's trained with such training data can make the context-specific prediction for future. This plot shows the forecasting performance that use the red line is the forecasting model that trained with synthetic training data incorporating the vaccination intervention, and the green line is without vaccination intervention. Then we can see that by incorporating the realistic intervention, we can make better forecasting. And this also enable the what-if forecasting. It means that if we want to tell the public policymaker that if you want to apply school closure in the next few weeks, then you can expect such kind of prediction of the disease dynamics in the next few weeks. So this is the highlight of the TDEFC framework. So the third challenge is the lack of robust behavior. As the epidemic dynamics change over the time, so the data is usually noisy and sparse. A single model usually won't perform consistently along the evolving time. So we consider the ensemble technique because the ensemble usually can reduce the overall risk of making a particularly poor selection. So we, along this research direction, we actually have two works. The first effort is made towards the COVID-19 case count forecasting. We employ the Bayesian model averaging ensemble technique to incorporate multiple models, include the AR, ARIMA, LSTM, the ensemble common filter, and also the compartmental SEIR models. And the plot here shows the individual model performance at different phases of the pandemic. So the color plot map shows the spread of the dominant methods in ensemble across counties for the particular week. And we can see that all the methods are important, actually. And each individual method contributes significantly across different regions and different weeks. And remember, we discussed the dynamic snapshot ensemble. So that work demonstrates the proposed method on classification task. Then we also apply this algorithm to make the COVID-19 forecasting. We use the LSTM as the base model and implement this dynamic snapshot ensemble. This plot shows that using the ensemble algorithm, which marked in the orange color, the model can perform better than the baseline model marked in the blue color. And there are other just a result regarding this forecasting that can be found in our paper. So above all, that's the research work regarding the epidemic forecasting. Then in section 4, I will present my current research works. So my PhD research work mainly deal with the numerical time series data, and we propose many framework to make a better forecasting. Then I just start to think whether I can combine the text information into the existing framework to further improve the forecasting accuracy. So I want to expand my current skill set to learn the NLP technologies. I joined the Boston Children's Hospital and Harvard Medical School in this clinical NLP lab. So they mainly focus on applying the NLP technology to extract the information from clinical narratives. And my research work, current research, there are two focus. The first one is to explore the learning rate schedule strategy for fine-tuning temporal relation extraction models using transformers. And the other work is to investigate new transformer-based architecture for long document classification, which also for the clinical narratives. I won't expand on the current ongoing works, but I will say that the proposed snapshot dynamic algorithm can also be applied to this fine-tuning strategy. And we already have some preliminary results to show that the algorithm work pretty good in improving this fine-tuning models performance. And in the last section, I will just conclude my research work and also briefly discuss my future research directions. So our research works have been applied in multiple real-time systems. So as a lead contributor, we participated in the CDC flu site challenge, which is to report the seasonal influenza forecasting along every flu season. And our method was the first to include deep learning models in the challenge. And during the COVID-19 pandemic, we have made tremendous efforts in the forecasting, and we produced the COVID-19 forecast and contributed to this CDC forecast hub, just using the basic model ensemble like I introduced in one of our research paper. So the results are also used as part of weekly briefing to the local federal sponsors, such as VDH. And we also developed our own forecasting dashboard. And on this dashboard, we present the weekly forecast for both influenza and COVID-19. Another highlight is that the proposed dynamic snapshot ensemble algorithm has been deployed in an on-land truck repair system. And by applying this algorithm, that the system performance got 10% improvement in both accuracy and correct consistency. And there is a patent based on this work that is forthcoming. So a brief conclusion. Then my works focus on AI for social good, and from theory to methods and to the downstream applications. The proposed new machine learning algorithm is generalizable and being applied in multiple research domains and applications. And one focus of my research is to investigate the accurate and explainable AI-based methods for epidemic forecasting. Then along this direction, that combining theory and deep learning models for epidemic forecasting is a lead contribution in the domain. And my current focus is exploring NLP techniques with the aim of facilitating my existing research works and also develop future research opportunities. Based on my previous work and current research, my future research revolves around the potential funding opportunities. A broad vision is to build a robust, fair, consistent, and explainable AI for social good. And there's three funding agencies that in my mind. The first is NSF, such as the RAPID, the NSF Korea or SEIR 2, and also NIH R1, K1, and CDC funding. There are three potential directions. The first one is the theory-guided machine learning for reliable epidemic forecasting. So this one is to extend my PhD research work. And actually, there are a lot more interesting topics to be explored in this direction. The first one is, as I mentioned, the what-if forecasting in epidemic by using the existing frameworks. That when we it is crucial for the public policymaker to make a better decision for the future control of the pandemic. So the what if forecasting is one of the focus. And then the second important question is the predictability of the epidemic data. So far we have proposed so many methods that can apply for epidemic forecasting. However, one basic question is whether the time series data that we are trying to predict is predictable or not. Because we have found that there are a large noise variance in the time series data. And the noise sometimes is larger than the time series data itself. It means that that part cannot be predicted. Then whether the proposed model is actually good or not, we compare with the other baseline. But if the time series data itself is not quite predictable, then the performance improvement that observed in our experiment may be not correct. So this is a really fundamental issue that we need to explore just to just in the future, we can make the real robust and reliable prediction in epidemic forecasting. And the other two interesting topics include the multimodal learning, which include the numerical feature and text feature, and also identifying the bias in the forecasting models. The second direction is to build the robust and consistent NLP for large-scale information extraction. When I apply the transformer-based models for my current research task, I found that there are many repeated efforts has been made when we apply the same model and the same method to different subdomain challenge. So so far the common way is when we do is to use the fine-tuning method, which is to leverage the pre-trained model and adapt the pre-trained model to the downstream data set. Then the fine-tuning strategy is the key point to bridge the gap between the general domain and specific domain. However, a transfer learning strategy may work in one domain, but may not work in another one. How to build the transferable fine-tuning methods that can work across implementations and applications? That is a really crucial and interesting topic to be explored, so that we can actually reduce the redundant efforts when we apply the same method to the different downstream domains. Then the second direction is to investigate the pruning algorithm for the deep neural network, which can also just to make a well adapt to the downstream applications using the existing model. And the third is to investigate the imbalance classification challenge using the meta-learning method. So the third research direction is the fair AI for social good. I actually want to investigate the fairness in AI system, but it is a wide range of topics because the fairness in AI system is defined differently in different domains. Then we just want to see at a macro level and a macro and micro. At different level of the system, what the definition of the fairness. And another interesting topic is to investigate the trade-off between fairness and privacy in AI system. One scenario is that for my current project, we actually have the data source from multiple institutes, multiple hospitals. Then we need to collaborate in some way to train a single model on all of the data set. That will have some privacy leakage risk. So we want to keep the privacy of the data, and we also want to build a really good classifier that use all of the data sources. Then how to keep a trade-off between the fairness in all of the hospitals, and then to also keep the data privacy. That is really challenging issue that to be explored. So I consider that be a very interesting point. Then at last, I want to thank to my advisor, Chen Maidaf, Tim and Gugana, and also all my collaborators so far, Anirudh Dipanjan, Brian, Adam, and Srini, and many others whose names are not listed here. That's all. Thank you. And welcome to any question. You can just ask me.
Okay. Thank you, Dr. Wang. This was beautiful, very well organized, and your PowerPoints look like artwork. So, and even though I'm not an expert, I think I followed at least parts of your presentation. So, I'm going to ask a question, but I have to tell you that I have my next meeting right at 12. They're already knocking at my door, so maybe somebody else will have to take over for me. So my question is really this. It's notoriously difficult to separate temporal and causal effects. I mean, the sun's getting up in the morning, right? Does that cause me to have breakfast, or is this just a temporal connection? So I don't understand how you're separating causal and temporal.
I'm not sure I understand the question, but let me try to answer you with this one. Here, you mean how to separate the temporal dynamic between the causal module and the graph neural network? Is that your question?
No, my question is that in principle, in theory, it's difficult to say if something is a temporal connection or a causal connection. So as the example I gave, when the sun rises up in the morning and then I have breakfast, did the sun cause me to have breakfast, or do I just have breakfast after the sun rises? How can you know which one it is, temporal or causal?
Well, yeah, that's really a challenging question. Thank you. But the answer, I actually don't know from this framework, because in our framework, we can see that, so the temporal feature can be learned by using such as the LSTM. And also in our framework, it's GNN based, but we also incorporate the temporal feature in our framework. So these features are learned where the hidden embedding. We cannot explain the hidden embedding just in this framework. Then regarding the causal feature, you said we cannot separate it. Yes, still in our framework, we cannot separate it. We cannot tell which is caused by, it is the causal feature related, which is temporal feature related. But we just try to embed these causal features, which is unknown previously to the deep learning model. We want to embed those unknown features into this learning process and propagate over the graph neural network, so that it can learn hidden in a hidden space. It can learn the causal feature from the simulation. We try to learn that, but we cannot distinguish it from the temporal feature.
Okay, thank you.
Sorry, I don't know the answer.
I didn't expect that you could, because this might be an unsolvable problem, but I just wanted to hear it for sure. Okay, I have only 3 minutes. Are there anybody else? Is there anybody else who wants to ask questions or take over the session? Any questions?
Yeah. Hi, Lijing. I am Haifan. Yeah. Hi.
Hi.
So I have one question regarding to the first work about the inconsistency in the model training, right? So
Yeah.
so what is the root cause the inconsistency?
Sorry. What is the rule?
The root cause. The root cause.
Cause. The root cause.
Yeah. What is the root cause that that's inconsistency? Yeah.
Okay. I see. Yeah. So there are actually many factors that lead to this inconsistent behavior. One of the feature is the random learning process through the optimization algorithm. I will give an example. So when we implement a simple deep learning model such as LSTM, then if we want to reproduce your prediction, you can set up a random seed, right? Then
let me go a little bit deeper. Basically, you say that you train one model and then you have new data, you train it again, and basically that for sure will cause the shift of the decision boundary, and you know, some may flip over the other basically side and so on. That is the inconsistency, right? That's the root cause of the inconsistency, because the new training data maybe have some distribution variance that cause the shift of the decision boundary. But that one is that one have been solved in, you know, like many other learning framework, for example, like a lifelong learning, and you ensure that the decision boundary will not shift given a set of you know, data point and so on. So what is the really like fundamental contributions of your work compared to those kind of like, you know, like existing work out there, for example, like lifelong learning or something, you know, like
yeah. Thanks for the question. So I think I can answer you from the different level of this challenge. When you said when the new data come in, so the data distribution may shift. So the model need to adapt to the new data distribution. We use continual learning. We use the active learning so that the model can continue to learn on the new data side, right? But that is at the macro level. At the macro level means that we actually can let the model to continue to learn on the new data. And then, so the new trained model can achieve good performance even the data distribution shifted. That's the macro level. That in our work, that we try to investigate this problem at a macro level. It means that for each individual prediction or input or instance, then a model that it trained across different generations. Given the same input, whether this model can behave consistently, right?
So basically that is they call it one of the problem there is the catastrophic forgetting problems. Basically you have a different generation, then some will forget something. So to solve that one, they have some constraints that a particular but why your ensemble model basically solve that problem is not clear to me.
So you just mentioned the new model that learn from the new data, they may forget some important things, so that given the same input, it won't give the correct prediction, right?
Yeah.
So the ensemble algorithm is try to like we show here. It is not the how to say that, just the intuition of the ensemble learning is that when we collect the local optimal model from the training process, actually each local optimal model will cover the feature space for some coverage, right? For some coverage of the feature space. Then another local optimal model may cover another part of the feature space. And this feature space may overlap or may not. When we apply the ensemble model, we actually collect all these local optimal model together. It means that in the ensemble learner, we obtain a greater coverage of the feature space. So that given even the model just trained again, so that we can just get a consensus for the final prediction because we have a greater coverage of the feature space. Does that make sense? So it just yeah.
Yeah. So maybe we can discuss more in our one-on-one discussions.
Sure.
Yeah. Thank you. Yeah.
Thank you. Thank you for the great question.
Any other questions from everyone? Or yeah, I think like we are over the time now. So yeah. Thank you very much for your presentation. It's very impressive. Yeah.
Thank you.
Thank you, everyone.